The Energy Regulatory Commission is now the Energy and Petroleum Regulatory Authority. EPRA is established under the Energy Act 2019 and regulates electrical power, renewable energy, and petroleum subsectors. EPRA's expanded mandate includes the regulation of upstream petroleum and coal. EPRA protects the interests of energy consumers and ensures that all players in the energy sector adhere to set business practices. We are here to facilitate access to sustainable energy for all. EPRA, quality energy, quality life.
The Kenyan government targets to universal access to electricity by 2020, with 60% of the 30% unelectrified population set to be electrified through solar power, mini grids, and solar home systems. Further, Kenya boasts of an electricity mix of more than 80%, which is more than 80% renewable energy. This is a great achievement. The progress in electrification using renewable energy in Kenya underpins the potential of developing countries to leapfrog ahead of the past practices to spearhead an integrated approach towards the development. This is by building a nexus between energy access and other development goals. Ladies and gentlemen, notwithstanding the highlighted progress, challenges still exist in the adoption of clean energy in the transport sector and cooking. Africa is still reliant on the unsustainable use of biomass for cooking. In Kenya, for instance, more than 60% of the population relies on the traditional use of biomass for cooking, with this more prevalent in the rural areas. In addition, with the integration of more and more intermittent renewable energy technologies, such as solar and wind onto the electric power system, system operators continue to grapple with the challenge of unmodernized grids, which are still operated manually. So questions such as how much of intermittent renewable energy technologies can be integrated to specific grids still abound. For instance, one of the key questions that faces us today is what is the levelized cost of energy of the technologies, taking into account the auxiliary and ancillary services required to support the integration? And how can the electricity network owners and the system operators leverage on the technology to improve on the system reliability and cut on the cost of operation? Other questions include which business model should be adopted to promote the uptake of distinguished generation technologies, or to promote the uptake of distributed generation technologies, including mini grids for rural electrification. I am confident that with the support of academia, the above problems facing our society in realizing universal access to energy for sustainable development shall be addressed. And this conference provides such a platform to share ideas and build on each other's strengths for a better society. Ladies and gentlemen, Kenya continues to strive towards building a robust policy and regulatory framework to support the growth of a sustainable energy sector. The Energy Act 2019, exempted to in March last year, is evidence of such documents that enhance transparency in the energy sector and creates avenues for private sector participation. Among the provisions that creates avenues for growth of renewable energy technologies include the provisions for net metering, open access framework that allows power wheeling and electricity retailing, and the promotion of energy efficiency technologies. The Energy and Petroleum Regulatory Authority is currently developing a number of regulations to support the implementation of the above provisions in the Act. Ladies and gentlemen, I wish to urge participants of this conference to take up the investment opportunities created by the Act and support its implementation by conducting targeted studies that could define the growth trajectory of renewable energy in Kenya and in the region. The subsequent benefits will have a ripple effect in the entire Kenyan economy and region. Once more, I thank you for listening to me and wish you fruitful engagement during this conference. I will be very keen on the outcomes for adoption in the promotion of renewable energy in Kenya. Thank you all, and may God bless you. That is the speech of Robert Pavel Oimeke. Ladies and gentlemen, I beg to submit. Thank you very much, Bwana Organizer.
Thank you. Thank you for that speech from Robert Oimeke. on the importance of renewable energy in Kenya, the challenges and our roles and opportunities in the development of these renewable energies. I think since he's not present physically or is not with us online, we will not be able to ask any questions on this section of the presentation. So, ladies and gentlemen, if you can allow me, we can move to the next presentation. And that was from ZDMI Bay. We can move to that. As I said, ZDMI Bay is a master's student in Moi University. And the title of her topic today is the evaluation of Kisumu County clay soil for plastic waste pyrolysis. Welcome, Zedi.
Thank you. Let me share the PowerPoint slides. Can you see my slides?
Yes, Zedi, if you can put it on presentation mode.
Okay.
Okay, thank you. You can start.
Okay, let me start. Good morning, all. The title of my presentation is Characterization of Clay from Kisumu County in Kenya for Catalytic Pyrolysis of Waste Plastics. The authors in this research are Mibei Chepchirchir Zedi, Professor Kumar, and Dr. Stephen Talai. I go to the introduction. Clay, I'll define clay. Clay mineral is a stony or earthy mineral aggregate consisting of hydrous silicates of alumina. Plastic when sufficiently pulverized and wet, but it is rigid when it is dry and vitreous when fired at a sufficiently high temperature. You find that clays also have other significant amounts of cations in the crystalline structure. Many types of clay in Kenya are in the group of montmorillonite and are highly contaminated with quartz. This was by Murithi et al. 2012. A study also was carried out in south of Nairobi City in Kenya that showed that the red soils in the area was mainly kaolinite in composition and polygenetic in origin, while the black clays in the area was mainly smectites. We also have the analysis of magnesium-rich clays in Amboseli Basin in Tanzania and Kenya revealed that the carbonate rocks consist of limestone and dolomite for Tanzania, and for Kenya they only contain dolomite. We have also the sepiolite, dolomite, and illite also find to be available in the samples. On my literature review, we find that there are several people who've done research on clay, and clay from Tharaka Nithi was analyzed, and the XRD results showed that the clay consisted of albite with impurities also like quartz and iron 2 oxide. Oswago 2016 analyzed the levels of iron in Kisumu County clay since it affected the clay's use in making high quality ceramics. Those are the few people that have analyzed clay soils in Kenya. And this clay is, I was analyzing on the condition that it can be used as a catalyst. And you find that a number of researchers also have done the same research on catalytic pyrolysis of plastics, and they've used several types of catalysts. This includes the following catalyst. We have iron 2 oxide, calcium hydroxide, FCC, natural zeolite, synthetic zeolite, red mud. We have ZSM5, HZSM5, and Y zeolite. And you find that all these catalysts that people have, the researchers have used, are conventional type of catalyst. So the clay soil that we are analyzing is actually a natural it's a natural zeolite. Sakata et al. Carried out the pyrolysis of HDPE by using 3 different types of silica alumina catalyst, and these were SA1, SA2, and ZSM5. And the obtained results indicated that SA2 catalyst with lower acidity produced maximum quantity of liquid oil at 74%, while ZSM5, which was of higher acidity, produced lower quantity of liquid oil. The catalysts improve the quality of pyrolysis products because some of the larger carbon chain compounds are adsorbed into the catalysts and broken down further into small carbon chain compounds. The catalysts increase the lighter fractions in the liquid oil, such as gasoline. So if you use a catalyst while doing the pyrolysis, you find that the liquid oil that you get has a better quality, and also you get the lighter fractions, which is gasoline. And this decreased the overall process energy inputs. The use of ZSM5 catalyst decreased the impurities such as solid residue, sulfur, nitrogen, and phosphorus in the produced liquid oil. The objectives of this study is to determine the elemental composition, crystallographic structure, and the concentration of specific metal elements in clay from Kisumu County. The justification of this study is that pyrolysis of plastic requires intense heat in absence of oxygen. Catalysts reduce the process temperature, thereby decrease the overall process energy inputs, and also improve the quality of pyrolysis products. The catalysts also improve, sorry for the repetition, the lighter fractions in the liquid oil, such as gasoline. And we find that the conventional catalysts are expensive, the ones that are already led in the list, and while clays occur naturally along the rivers in Kisumu County. And that actually motivated this research, because these are actually clay soils which are found naturally in the rivers. The experimental procedure: the sample was dried and cooled. The dried samples were then ground into fine powder suitable for use in XRD, XRF, and AAS analysis. And maybe to explain briefly is that for XRF analysis, this was actually to determine the percentage composition of the element in oxide form, and this was displayed on the screen of the machine after the analysis. The X-ray diffraction analysis. XRD revealed detailed information about the chemical composition and crystallographic structure of the natural clay sample. And for AAS analysis, this was to determine the concentration of specifically alumina and silica in the clay samples, because the most important elements necessary for clay to be used as catalyst are alumina and silica. I go to the results. This is what is on the screen are the elemental analysis of clay using XRF machine. And you find that from this, the XRF gave us that silica is actually the highest in concentration at 64% by mass, and alumina is the second one at 16.3%. We have other elements which are like iron 2 oxide at 9%. We have potassium at 4%, and the rest are actually trace elements at very minimal percentages. So this is what was found from XRF. From XRD, this was the mineral analysis of clay using XRD. The diffractometer produced signals on the screen, and the names and formula of minerals were also. The XRD identified the major mineral as orthoclase, as you can see from the graph. This was orthoclase, and the chemical formula has the alumina and silica as part of the elements in the clay soil. This formula established that alumina and silica are structural components of the clay. For AS analysis, it was only to determine the concentration of aluminum and silicon in clay. And as these are the results. The findings, the discussion, we find that XRF results show that clays from Kisumu County, Kano Plains, have silica at 64% and alumina at 16%, and iron 2 oxide, which is 9%. These are the major elements in the clay. The silica alumina catalysts are amorphous catalysts having Lewis sites as electron acceptors and Bronsted acid sites with ionizable hydrogen atoms. The acidity of the catalyst was determined by using mole ratio of the silica divided by alumina. Acidity of the catalyst affects the production of liquid oil from plastic pyrolysis. The lower the acidity, the higher will be the production of liquid oil from pyrolysis. The mole ratio of Kisumu County clay was found to be 3.96, which is lower, and this means that if it is used as a catalyst, it will produce a higher amount of liquid oil from plastic waste pyrolysis or any pyrolysis process. From the XRD analysis of the clay, this was identified, XRD analysis of the clay identified the major mineral as orthoclase, and we find that this is a layered mineral comprising of tetrahedral sheets of silica, which are linked through oxygen atoms to sheets of alumina. And as I said previously, this actually established that they are the structural components of the clay mineral. The significance of the findings. Clay have very fine particles that yield very large specific surface areas that are physically adsorptive and chemically surface active. The clay minerals carry excess negative electric charge owing to internal substitution of silica ions by lower valent cations, and thereby increase internal chemical reactivity in chemical combination and ion exchange. These characteristics contribute to the properties which are of technical importance, like being used as a catalyst. The peculiar crystalline structure of clay minerals generates a capacity of reversible exchange with organic or inorganic cations. The exchange of specific cations generates active centers in the clay minerals, making them catalysts, which can then be used for pyrolysis of plastics. In conclusion, we can say that clay soil can be used as a cheaper catalyst, and this will reduce the production cost considerably, and it will also improve the fuel quality and overall process optimization. The clay from Kisumu have appreciable amount of silica and alumina, which are the major constituents required for a catalyst to be used in pyrolysis of plastic waste. These are my references. Thank you, and God bless you.
Thank you, Zedi, for your presentation. Although your presentation was not moving on my screen, I don't know whether it was only me. But we are open for questions, members. If you can, if you have any question for Zedi. So as members, as you think of your questions, Zedi, I'd like to ask a question on the acidity. You gave the acidity of the clay as 3.96, What is the optimum
Yes.
acidity for catalysts for pyrolysis? Is there an optimum figure? Is there an optimum figure for acidity?
I can say there's no actually an optimum, but you find that at lower acidity levels, you can actually get a higher level of liquid oil being produced. But because other catalysts have higher acidity, like even up to 10 or even 15, and from literature, I found that these catalysts actually produce a less amount of liquid oil when used for plastic pyrolysis.
Okay, thank you for your response. Members, any pressing questions?
I can see a question on the chat from Gad Mugaga. Can you hear me?
Yes. Can you?
Gad Mugaga is asking, what other factors affected the output of pyrolysis oil other than the lower acidity? Okay, I think this is a broad question on pyrolysis. Yeah, I will respond to that. This is a question on pyrolysis of oil, and you find that in the pyrolysis of oil, there are several factors that affect the output of oil. We have the amount of catalyst used, the temperature used. We have the time of residence. There are several factors, and also the amount of catalyst that you use. So I think this is a topic on pyrolysis, and as I've said, those are the factors that affect. We have temperature, the acidity of the catalyst, the amount of the catalyst that you use, the time of residence. Yeah, those are some of the few.
Okay, thank you. Any other questions? Anybody else with a pressing question?
Yeah, I can see a question from Kiptiemoy K. Are there other ways of or methods of increasing catalytic performance of clay? Yes, I can say there are, like increasing the surface area, making them very fine particles. There is also one of them is actually increasing the surface area. We have also you can increase the catalytic activity by purifying the clay because it has impurities. Yeah.
Okay.
So I only concentrated on determining the silica and alumina levels. And so maybe I'll also look into the other ways of increasing the catalytic performance of the clay.
So thank you for your response. Do you have any other questions? There is a question from Eric Minda. What is the lowest acceptable acidity you can recommend for the catalyst? ZD, can you respond to that?
Yeah, I can say, okay, from literature, I read that at lower acidity of 5 and below, that is the recommended acidity of the catalyst that will actually produce a higher level of liquid oil when used in pyrolysis. 5 and below.
Okay, thank you for that response. I think members, if there are no more questions, then we can move to the next presentation. Thank you, Zedi, for your good presentation and the response to the questions. You may stop sharing.
Thank you.
So the next presentation on our program is from Samuel Kusasira. Is Samuel present? Samuel Kusasira. Do you have Samuel Kusasira?
I can hear somebody talking from background.
Hello?
Hello, can you increase your volume?
Okay. The volume seems to be higher. Hello?
Yes. Samuel.
Hello?
You are still breaking. If you can still check your volume.
Okay. Good morning. Hello?
Yes, now we can hear you, Samuel.
Okay, thank you so much. Is my PowerPoint shared?
You can start sharing your PowerPoint.
I have shared. Is it visible?
It's not visible yet.
Okay. I go to share. Share. Then is it now visible?
Yes, it's loading.
Okay, thank you so much. My name is Samuel Sasera from Kampala.
I don't know about the other. It's loading.
Is it loaded?
Yes, it's there now. We can see it. You can see it.
Okay, my name is Samuel Sasera from Makerere University Business School, Kampala. Founder of 4Energy Connect Uganda Limited, co-implementer of our smart energy application. The topic for study is a time series analysis of the socio-economic determinants of carbon emission levels.
Oh, sorry.
Samuel.
Sorry.
Sorry.
Yes.
We cannot see the presentation.
Yes, please.
We cannot see the presentation. Please share it again.
Am I there?
Yes, you're there now.
Okay. So I was saying it's a time series analysis.
It's not in the play mode. Could you press slideshow and play? Thank you.
Thank you. I think I must be missing that. Am I able to play it from the Microsoft Teams or from my computer?
You play it from your computer, just
like
a PowerPoint presentation.
Go to slideshow.
Just go to slideshow.
All right, thank you. Okay. So my name is Samuel Sasera.
Sorry, it's not work.
It's not there.
Not work. Did you press the slideshow and then play show?
Yes, I did.
Press F5, please.
If it not work, please press view, the up button view in a PPT. view. Press view. Can you press view? The button view.
Okay.
View is at the top.
At the top of your PPT.
I think it's visible. I don't know whether you're able to
Yes.
see it.
Yes, Samuel, it is visible, but we want it in a full screen. So you go to slideshow and play the slides.
I am playing them.
Yes, it's played, but we want it in a full mode view.
If it does not work, you can try another way. Another way is press the view.
That
Please.
is.
Please
I
go
press
to
which
the.
Control and what? Control.
No, just F5.
I'm having trouble with that.
You can
F5,
exit. You can exit the full screen from your computer. Try again. Then try again. Press the view button, not the slideshow. Maybe the slideshow in your computer is not work.
Oh.
Can you do that?
No, I have failed to do that.
Oh yeah. I
Yes.
can. I mouse the
Your
mouse.
mouse.
I
Your
see your
mouse
mouse.
is moving. Just
Move
move it
to
to
the view.
slideshow. Or
No.
the view.
Maybe slideshow not work. Maybe.
Okay.
Yeah.
Just
Maybe
go
the
to
easiest
view.
is try F5.
View.
Try pressing F5.
F5 not work. I know.
No.
You can press the view. Try press the view on the button, on the top button. Can you see? Can you see the view button on the top of your presentation PPT?
I'm not sure.
Yeah. Move your mouse to the top.
But I don't
Yeah. Move your I can see. Move to the top.
Ameenda na watu wake waende to the right room. Oh, sawa.
Can you move your mouse? Can you?
Oh yeah.
Yeah, to the view. Do you see the top button view?
I'm not seeing the top button called view.
VIEW.
Home, insert, design, animation, slideshow, review. Then there is view at the top.
Okay. Let me first remove the slides. Thank you. Let me go there. Okay, view.
View. Yeah, press view. Press. Yes, good.
Okay.
Yeah, press.
Click on it.
I press.
Yeah.
I have clicked on now.
Yes.
Okay.
Press view. Yes.
Slideshow.
Then press reading view.
Go to the slideshow. Go to the slideshow.
Slideshow.
Yeah. Slideshow. Yeah.
That's it.
Press the slideshow.
Yeah, slideshow.
Are you able now to see?
Press it.
I have already.
Your screen is supposed to be full because you can see the one which is on the side. The whole PowerPoint is supposed to be full in your screen.
I don't know why it is not showing full on the screen. It's cut out.
It is easy way. Just say shift F5, please.
I shift
F5.
F5.
Yeah.
It's the same thing.
Yeah, your computer is not.
Then continue. You can continue. Maybe you can continue like that. Let's continue.
Okay. Sorry. My name is Kasera from Mary University Business School, founder of For Energy Connect Limited, and a company which is supposed to implement the For Smart Energy e-commerce application. The topic, what I'm talking about today, is the time series analysis of the socio-economic determinants for carbon emission levels in Uganda as one of the emerging sub-Saharan economies. Carbon emission is a worldwide threat due to its effect on climate change, global warming, respiratory health challenges, and among others. And at that, Uganda is a member of the United Nations Framework Convention for climate change and a signatory to the 1997 Kyoto Protocol and 2015 Paris Agreement. But also internally, the country has parastatals and authorities, which include the National Environment Management Authority and the Ministry of Water and Environment. However, with the presence of all those in place, Uganda has continued to experience a growth in carbon emission from 53,000 gigatons in 2005 to 90,000 gigatons in 2015, according to the Uganda Climate Action Report. It is notable also that the Ministry of Water and Environment predicts an increase in carbon emissions after 2020 from the consumption of petroleum and gas. Additionally, in the same period we are studying, Uganda's GDP grew by 11.7 billions from 1990 to 2012, according to the Climate Link. In the same country, the implementation of the East African Trade Protocols has taken on with the major ones starting in 2005, which meant that the country had to move away from the unilateral trade liberalization to trade integration with its member states. Why is this important? We realize that by the introduction and implementation of the East African Trade Protocols, the export and the import diversification widened, and also we have been able to see a tremendous reduction in non-tariff barriers. And additionally, the free market
Samuel, if I may interrupt you a bit.
Okay, please.
Members, are the slides moving?
No.
Can you see the movement of? Is still the title page?
Yeah.
They're not.
But yet to continue to see them.
Samuel, can you start? Can you try stopping your video? We can only see the title page.
Let me stop my video.
Just stop your video, then try to move to the next slide.
Okay. So from here, are we able to go?
I'm still okay. Now you have moved to the next one. Okay. Yeah, maybe you can just now continue.
I continue. All right.
Yes,
From the introduction, I was talking about why is it important, and I was saying that the East African Trade Protocols that have been implemented have widened the export and import diversification, but also we have been able to see a reduction in non-tariff barriers, tremendously being implemented by Uganda for its member states and other nations that are in trade with it. There is a growth in the free market, which implies that it requires increased productivity and also energy consumption for us to be able to meet the requirement. However, previous studies do not give empirical evidence about the long-run effect of gross domestic product growth and then fuel consumption, trade protocols on carbon emission levels in Uganda. It is important to note that the population size impacts significantly on these dimensions in the long run. For example, when you look at Ugandan growth is 3.7% annual population growth rate, which means we cannot be able to understand the impact of these variables using an aggregate scenario, but rather adopt the per capita values to be able to assess the effect. So, what is the objective of this study? The objective of this study, the aim of this study is to ignite an action-oriented discussion with a millennium mindset on strategies to decarbonize the economic playground or the environment. And the specific objectives, we are going to assess the effect of real gross domestic product on carbon emission levels in Uganda, and also we want to assess the effect of fuel consumption on fossil fuel consumption on carbon levels in Uganda. And the last is to assess the effect of open access trade policies or the East African Trade Protocols on carbon emission levels in Uganda. The methodology adopted in this study is a derived steepart model which is a stochastic impact on environment by regression on population, affluence, and technology, which
Samuel,
was initially. Yes, please.
I am not seeing your screen moving again. It stopped at rationale.
I think I have to be going there and back.
Can you try?
Oh, goodness.
Can you try? Can you try again?
I think I'm supposed to be operating from. Okay. Is it moving?
We are still seeing the rationale only.
Up now.
Yes.
I think
Members, what can you see?
Yes, maybe due to the network issue, that's why his screen is moving slowly. You should maybe just give it time, a little bit more time for it to load.
Oh. This is very tragic.
Now we are seeing aims and objectives.
Okay. You see now aims and objectives. I think it takes time. Okay. So I am going to see what that means, but the aim is to ignite the action-oriented discussion with millennium mindset and strategies to decarbonize the economic background, which is the environment. Our objective number one is to assess the effect of real gross domestic product on carbon emission levels in Uganda. The next one is to find out the effect of fossil fuel consumption on carbon emissions in Uganda. And the last one is to assess the effect of East African trade protocols on the carbon emission levels in Uganda. Our methodology is a STPAT model, which was initially non-linear, but we linearized it by and also stabilized the mean by introducing the natural logarithm. And the time series study that we are carrying out is based on secondary data from World Bank. I have been able to analyze the data using Stata, which allowed me to undertake the pre-estimation diagnostics like normality, multiple linearity, boundness test, among others. After carrying out the pre-estimation diagnostics, we found that our results were plausible, so we could be able to go ahead and estimate the model. The model adopted is an autoregressive distributed lag error correction model, which was estimated to assess the long-run relationship or non-stationary variables at level. It was also able to carry out post-estimation diagnostics, which indicated the reliability of the findings. Thus, I was able to carry out the interpretation and the conclusion of the findings. So, according to the results, we realized that the model is able to explain 52% of the variations in carbon emissions per capita. And also the error correction model was effective. That means our model is not suffering from statistical errors. And we found out that the real gross domestic product per capita is significant in the long run and has a positive gradient. However, fuel was insignificant, but there's a intercept with negative gradient.
Can we hear Samuel?
To significance. Hello. Hello. Hello.
Yeah, we can hear you.
I was saying, and also we realized that studying a positive intercept. However, the short-run analysis indicates that in the short run, there is no convergence among the variables. That means you cannot be able to assess the effect of real gross domestic product per capita, fossil fuel consumption per capita, and the trade policies on carbon emissions in the short run. Therefore, we are going to concentrate on the interpretation of the results in the long run analysis because they tend to be convergent in the long run. So, what is in our finding? We realize that our equation is a linear function. That means
Hello,
carbon emission.
Samuel. Your
Again, you're not
screens are
seeing the
still,
slide?
the slides are not moving and your voice is breaking.
My
Yeah,
voice
it
is
does.
breaking.
Yeah.
You're able now to see them? Hello?
Yes, we can see.
We are,
I can
we are
see,
still at
but
methodology.
yeah.
You're still on methodology?
We have not moved to results. Yes.
This is too much. It is getting, I think I need to change your computer. It seems, but I'm not, let me present. Are you now seeing the results?
It's not your computer, but the network. I think so.
Okay. Are you now seeing the results?
Yes, we can see the table.
Okay, you can see the table with the results.
With some statistical results.
Okay, I was saying when you look at the R squared, this model is able to explain 52.5% of the variation in carbon emission per capita. And according to the adjustment term, because I've used the error correction model, the error has been significantly corrected when you look at the 0.05. But also the long run relationship of carbon emission and these other deterministic variables it tends to significance. That means we see the real gross domestic product per capita significant and it has a positive gradient. Then when you look at the fuel consumption per capita, it's insignificant. However, it comes out with a negative gradient, which is very key. And also, the dummy variable, as we move to the long run, tends to significance and has a positive gradient. However, the short run analysis below does not show any convergence among these variables in the short run. That means in the short run, you cannot be able to assess the effect of a real gross domestic product, fossil fuel consumption, and the implementation of trade protocols on carbon emission in the short run. And that's why I said we can only now, based on the long run analysis, to be able to interpret our results. So we shall use this other side of the table to be able to go for our discussions. Is the screen now visible?
Yes, the results are visible.
I'm on discussion now.
And, for me, I'm still at the results.
You see the results.
Unless the other members can see the next slide.
Discussion.
Okay, just continue.
Yes, it's now visible.
From our findings, objective number one was to assess the effect of real gross domestic product on carbon emission levels in Uganda, and we found out that 1% growth in real gross domestic product per capita leads to a 2.217% increase in carbon emission levels, which implies that there is a higher proportionate increase in carbon emission compared to real gross domestic product growth per capita. But what explains this? This is explained by the traditional ways of generating GDP that are experienced and practiced in Uganda. For example, when you look at this picture, I don't know whether you're able to see my slides. There is a picture of someone who has cleared the field, and they have not only stopped at removing the decarbonizing agent, which is the green cover, but have gone ahead even to burn it. Now, in the process, we end up emitting more than how much we actually gain in terms of the real gross domestic product per capita. Additionally, Our objective number 2, we wanted to assess how fossil fuel consumption affects carbon emission levels in Uganda. I hope you can be able to see the slide. Are you able to see the slide?
Just wait for it to load. Give it maybe a few seconds.
We are still seeing objective 1.
Are they loaded? Hello?
Just a moment.
Are they loaded?
Yes, we can see objective 2.
Okay, correct. Objective 2 is we wanted to assess the effect of fossil fuel consumption on carbon emission levels in Uganda, and we realized that a 1% increase
Just go on.
A 1% increase in consumption of fossil fuel products per capita leads to a 0.19% reduction in per capita carbon emission. Now, this is a very unique finding from what we have already thought of. But there is empirical evidence. We find that biomass fuels like wood, charcoal, and briquettes service 93% of Uganda's energy needs compared to 6% oil consumption. And this means that we emit more from wood and charcoal and briquettes than we emit from oil consumption. However, the World Liquefied Petroleum Gas had the research in India, and it indicated that LPG gas emits 60% fewer gases than the electric oil cooktops, and it emits 50% lesser gases than biomass stoves, and 19% fewer gases than kerosene stoves. That means as people adopt more of liquefied petroleum gas for the needs of lighting, if we have that system for cooking, we are likely to actually reduce more of carbon emission instead of using the current biomass fuels that we have that are dominant in our systems of emerging economies in sub-Saharan Africa. The next objective, I don't know whether it has already over there, but the third objective was to assess the effect of the trade protocols on emissions in Uganda. And according to the third finding, we realized that the implementation of the current trade protocols leads to a 0.271% increment in carbon emissions. Now, one of those trade policies that have been implemented in 2008, East African communities and the countries within launched the removal of non-tariff barriers. And what does this mean? This means we cannot put a total ban on importation of some products, which allows many products that are not environmentally friendly into the economy. It allows free access. That means that anyone can go anywhere at any time. And we cannot be able to monitor which commodities are good or are decarbonizing or are carbonizing, because we have a non-tariff barrier which would work so much to ensure that we mitigate any importation and exportation of products that are not environmentally friendly. Now, such policies, we are realizing that in the long run, they have a positive effect on carbon emissions, which if the talk is to decarbonize, they would have a negative impact. So what is the importance of our findings? The findings act as a basis of us starting to think on integrating climate change mitigation strategies in international trade discussions. As we sign trade treaties and agreements, we need to incorporate climate change and carbon emission measures. Then also the study demonstrates the need to track environmental damage caused by gross domestic product growth in national accounts. And eventually we can see how governments be able to evolve climate change and carbon emission strategies in the budgeting process of the country. And lastly, the findings are an evidence of that developing countries can in the near future reduce carbon emission through promoting the liquefied petroleum
Hello.
gas. Yes, please.
Should that be on another slide or the same slide?
No, it's on the same slide.
On the same, okay.
I have put it on the same slide.
Okay.
So I was saying the study is an evidence that developing countries can in the near future significantly reduce carbon emission through promoting the liquefied petroleum gas usage other than using charcoal, briquettes, and wood. In conclusion, our study, we see that there are long run and short run mitigation and interventions that we can be able to do to address the issue of carbon emissions in Uganda by far. For example, one of them, we need to think of green energy investment in mini-grid solar, investment in liquefied petroleum gas usage, and if we cannot afford for some communities that are remote, at least at worst, let's invest in energy saving stoves. Secondly, there is need to sensitize communities about green agricultural practices other than using the rudimentary way of burning shrubs and agricultural remains. We can sensitize them and help them be able to turn those remains into fertilizers that can be used for agriculture, but also resold for generating income. In the medium and long-term intervention, we may need to integrate climate change and emission mitigation measures in trade policies and national accounts, as we said. But firstly, we have to ensure and invest in training our human resource. We could have engineers who are able to transform available resources into sustainable energy sources, such that we have a sustainability of energy supply in our countries. Also, there's need to reduce taxes on clean energy products by government, and also there's need to start a conversation of carbon tax inclusion on imported and exported non-organic material. Finally, when you come back to the economic playground, which is environment, where can you invest? In Uganda currently, I think I may need to ensure that as the final slides loaded, the current economic playground, we realize that 90% of fuel that is used in Uganda is serviced by firewood, charcoal, which is biomass. Yet the lives that people are living are not those that are sufficient and sustainable according to the Sustainable Development Goal 7. We can go solar. As investors, we can advocate for the use of solar as academicians, and we see how we can be able to support communities to engage and be able to use greener energy products. And also lastly, as we see the grid access at 19%, we still see governments invest in thermal power plants, which are not only not efficient, but they're very expensive, yet they cannot achieve the total connectivity to grid electricity. Why can't we invest in mini-grid solars and save some fuel, oil, for the future generation, where these mini grid solars can be able to support farmers in irrigation, support remote or village communities with the lighting and the heating needs. And also we ensure that we keep our environment carbon free, or we are able to reduce the carbon levels in our environment. Thank you so much. I apologize for the technical errors, but that was my presentation. Thank you.
Thank you, Samuel, for your presentation. Despite the technical challenges, I think we have managed to get in something on the time series analysis you have conducted. Now, members, we are open for questions. If you have any questions. Dr. Jerry Ochola. Dr. Ochola, you can ask your question.
Okay, sorry, Prof. I was trying to unmute myself.
Okay, go ahead.
I have two questions for the presenter. One, you talked about time series, but most of the things I saw in your presentation was that statistical analysis per se. So at what point did you use the time series? And what was the approach of which parameters did you put in your algorithms? Because you talked about the nonlinear model that I couldn't see in the slides. That's one. And two, what percentage of your results does the model explain? You talked about a percentage that I couldn't hear so well.
Thank you. All right. According to the time series analysis, I used, that's why I said I used the auto-regressive distributed lag error correction model. It's a model in time series that we use to study nonlinear series of our variables. So that explains the time series. About the nonlinearity, I think because of the technical error, the slide maybe was not visible, but there was the Stipart model, or is a nonlinear series. And I said we linearized it by using natural, according to the percentage of explained by the model, is a 53.3% of the variation in carbon emission due to the deterministic variables. Thank you.
Samuel, what is the percentage?
Yes, 53.3.
83.3.
No, 53.
53. Oh, so I saw it correctly.
Yeah.
So at 53%, I think then your discussions are exaggerated. You cannot talk about that being a model that explains better, because that means that most of the model explains less than actually what you are talking about. Because it's common norm that your model should explain at least 63 or to 65%. 53 should be very low. So I think you should look into that. It means that I think I noted something here. You are saying that there was a low error in the model when you are trying to explain the discussions. That statement is to me is exaggerated. At 53%, you cannot talk about low error. Low error you talk about when you have close to 90%. So I think you should remove that statement from your manuscript.
Okay.
Thank you, Chair.
Thank you so much.
So thank you, Dr. Chola, and thank you, Samuel, for responding. Dr. Talai, you have a question?
Yeah. Thank you. My name is Dr. Talai from Mu University. And first of all, I would like to thank the presenter for trying to articulate the point despite the challenges that he had in presentation. So now I ask to the presenter is that the choice of the topic and the content look to be out of phase, because I was expecting more from non-formal sector or industries, because we know that Uganda, just like any other developing countries, is struggle. I mean, they try to use informal sector in terms of their materials. Like I say, we have these burning of tires, binding wires, and other activities there. But now the content is more of alternative source of energy. So I would like the presenter to respond on how this particular study accounted for the carbon emission from non-formal sector. Thank you.
Thank you so much, Dr. Tanai. And I really did not account for the non-formal sector because of the challenges of it, even being tracked in the gross domestic product, because of the issues of data availability. Sometimes such things are not tracked in the national accounts, and it's always an error that we get when we use the secondary data from sources. So since I use secondary data from the World Bank, as such, things may not have been incorporated into. Thank you.
Okay, thank you. So that means that now you realize that the choice of the title of this particular research, as in you are saying, socioeconomic determinants for carbon emissions levels. So in this case, it's out of phase to the study of how this particular research was looking at the findings. So it's out of phase. So maybe you need to look into that. Over to you, Chairman.
So thank you, Dr. Talai, for your observation, and I think Samuel will take that into account. Members, I think because of time, we'll need to move to the next presenter. Thank you, Samuel, for your presentation, and you can stop sharing now. So, members, our next presenter is Cosmas Kosge. Cosmas, you are present?
Yes, I'm present.
Samuel, can you stop sharing? Okay, Cosmas, maybe you can start sharing your presentation.
Yes,
So Cosmas is going to present on redox potential advances of quinone derivatives for energy storage applications. So you may share the presentation and start.
So I've shared. I think it is now loading. So let me know if when you can see. Can you see my presentation?
Yes, now you can see. You can put it on a presentation mode.
Okay, yes, I'm doing that. Is it now on presentation mode?
Wait a bit.
Not yet. Not yet.
Okay, okay. So let me know if it is on presentation mode. I've already done that.
You went to slideshow from the beginning?
Not yet
Yes.
on our screens.
Okay. Maybe it's loading. Caro, is it now on presentation mode?
No. Just go to view. And then, can you click on slideshow? Yeah. From beginning, just click on from beginning.
Okay. So I hope I can from beginning. Can you see my mouse?
Can you click it?
Okay. Is it now okay?
It's not on full screen mode. Just go to view, click on view.
View, then I've clicked on view. I hope you can see.
Reading view. Click on reading view. After view, then reading view. Click on reading
Okay.
view.
I've done that.
Yeah, now you can go.
Okay. So I hope you can also hear me. Okay, my review is about redox potential advances of quinone derivatives for energy storage applications. So this is a review paper. One speaking is Cosmas from School of Engineering, Moi University, a PhD student. So on to my next slide. Just an outline of what I will talk about. I hope it is on the second slide now. So I'll make a reference to quinone's molecular structure, its electrochemical behavior, quinone redox predictions, and the strides made in predicting its redox potential computationally. Then also the electrolyte factor, the applications where quinone is applied, and finally, conclusions. So on to my next slide, quinone's molecular structure. So quinone is made up of 2 oxygen atoms, and there are 3 moieties of quinones. One of them, which is made up of 1 moiety, is benzoquinone. With 2 moieties, we have naptoquinone, and with 3 moieties, we have anthraquinone. So quinone can be, its electronic behavior can be altered by attaching other atoms on these regions indicated R1, R2, all the way to R8. So functionalization or attachment can be made one at a go, or maybe all the regions indicated R can be, an attachment can be made with another atom, or maybe some group of other compounds or molecules. So, for example, electron donating groups, e.g. amine hydroxyl shown, has been found out to show a decrease in electron affinity, hence low redox potential. So for low redox potential, this one can be utilized in the negative side of a battery due to its low redox potential. So on the other side, we have the electron withdrawing substituents like nitro, potassium, and sulfonate. These ones have been found out to show high redox potential. So for high redox potential, this can be utilized on the positive side of the electrode. So the electrochemical behavior of quinone. Quinone is known to undergo a redox reaction to give hydroquinone, which involves 2 electrons and 2 protons. So for a battery, we require the release or we require the release of maybe electrons and protons to be utilized in our battery. So on to my next slide. A small background on quinone. So quinones can act as pendant groups, which are shown on as red circles. These are quinones attached onto a conducting polymer. So this can be, yes? Hello?
Sure.
Hello? Anyone?
Yeah, just continue.
Okay. So I was saying quinones shown on as red circles here, they can be attached as pendant groups onto a conducting polymer. So when its redox reaction takes place, the electrons released can be tapped onto a conducting polymer and later on transmitted to a current collector. So there are 3 reasons why quinones are attractive targets for electrical energy purposes. One of them is that it is involved in 2 biological processes, that is photosynthesis and respiration. And in these 2 processes, for them to take place, there should be an electron transfer. So the compound which is responsible for this electron transfer is quinone. So this analogy has been utilized in the makeup of a battery. So number 2 is that quinone has a stable redox chemistry, and also it is organic in nature, to mean it is sustainable. That is, it's unlimited and also clean to our environment. So this makes quinones attractive targets for electrical energy purposes. On to my next slide, the research on quinones. Research focus.
Sorry, let me interrupt.
Okay.
Please let us all mute our microphones. Let us all mute. Let us go on mute mode except for Cosmas, who is presenting. You can continue.
Okay, I hope everyone now is quiet. So research on quinones takes place in three subcategories. We have DFT modeling or simulation. So from these simulation results, suggestions can be made so that organic synthesis can be made from these suggestions of DFT modeling. And finally, electrochemical test is done to make these suggestions or research results practical. So thereafter, a sustainable battery can be made up from the results. So what the battery shown here is a redox flow battery, which is made up of quinone. So we call it sustainable because quinone in itself comes from our plants. And we've talked about it is unlimited and also clean to our environment. So my next slide will make reference to computational studies which have taken place. Few computational research studies to date have been done. For example, Air et al. 2015 identified redox potentials of about 300 quinone derivatives and predicted a redox potential of above 0.7. And they suggested possible lists to be synthesized. So a lot of work on synthesis is currently taking place, and a few of them have been tried out or onto the electrochemical test. So DFT or computational studies have given many results, but what needs to be done or what is taking place more now is actually the synthesis. So the DFT findings, some of the findings which guides the synthesis as such is it has been found out that solubility can be enhanced in quinone by making or by attaching other atoms on the regions which were indicated, regions R1 to R8 as we had seen before, and this is key in improving the new quinone electrolytes. Also, it has shown an increase in redox potential, and also new active redox species have been shown to be possibly used in a battery. For example, we have two, which I had also made reference to. One is substitution with electron donating group, e.g. amine hydroxyl, shown a decrease in electron affinity, hence low redox potential, giving a guide to the negative side of a battery. Also, quinone electron withdrawing substituents, species which have been suggested, e.g. nitro, potassium, and sulfonate, shown high redox potential. So attaching these groups on the sides of quinone have shown a new active redox species which can be synthesized as such. So further DFT findings, quinone electronic properties would be altered, e.g. with chemical bond of lithium oxygen. And then also during discharging process, as it is known that as lithium atom number is increased, there is a decrease in the redox potential. So it is important also to talk about the electrolyte factor, because apart from the positive electrode, negative electrode, we also have the electrolyte in a battery. So electrolyte, the best one is one with low temperature operation and also high on ionic conductivity. It has not been achieved from non-organic based electrolytes. So which means as we speak, more effort needs to be done so that an electrolyte with these two properties can be achieved. When we talk about acetonitrile, which is a solvent, which can be part of an electrolyte, acetonitrile is known to have three properties. It has good ionic conductivity, decent dielectric permittivity, and low viscosity. So specifically on acetonitrile, because we have an interest in studying more on how to incorporate or how to use acetonitrile, which is known to be aprotic, which means it doesn't have ready-made protons and electrons which can be utilized in a battery. But adding an acid or a protonated base can make it one of the electrolyte components. So acetonitrile has a limitation. One, is that its inability to form proper solid electrolyte interface on both graphite electrodes and lithium metal. So quinone versus electrolyte. There is a limitation of quinone in that quinone dissolution in electrolytes is due to two reasons. One is that it has low molecular weight, and also we have it being hydrophobic in nature, or its hydrophobicity, which means it is repelled or failure to be attracted. So this limits the life cycle of lithium-ion batteries, which equates to capacity loss during repeated steps of charging and discharging. So suggestions have been made to overcome this dissolution of quinone in an electrolyte. So remember, quinone, as I had said, can be attached as a pendant group into conducting polymer, and also it can be self-assembled onto a solid electrolyte like platinum. So some of the suggestions made to reduce this dissolution are functionalization with 2-lithiocarbonyl and also methoxyl groups, and carbon-based conducting nanomaterials. Another way which dissolution can be overcome is use of solid electrolytes, also use of quinone-based polymers, and pi-pi interaction, that is non-covalent interaction. So we also did something on redox flow battery, because practically quinone has been incorporated into a redox flow battery. There are two systems of batteries which have been developed, that is lithium-ion battery and redox flow battery. So a little redox flow battery has two tanks separated. That is an anode with anode particles and cathode particles. So unlike the lithium-ion battery, which both particles are in one tank, for redox flow battery they are separated, and the particles are pumped onto a separate place whereby current is collected. Now, it is possible to scale up the energy storage density of this battery by adjusting the external size of the tank. So doing this means the energy density of this battery can be improved. Also, solubility and redox potential of reversible redox active components govern the energy density. So it is not only the size of the tanks, we also have solubility and redox potential of the redox active components. So quinone being reversible redox active components, these two properties can be tuned, that is solubility and redox potential, which we can make reference on our next slide, which I'll talk about quinone for redox flow battery.
Cosmos?
Yes.
Just wind up in the next 2 minutes.
Okay. So couples of quinone and hydroquinone identified as candidates for interest for metal redox flow battery are due to three reasons: the good solubility in the aqueous solvent, earth abundance, and fast kinetic rate constants of charge transfer. So solubility and redox potential of quinones can further be tailored by introducing functional groups such as hydrophilic, also electron withdrawing and electron donating groups. Quinones as such, apart from rechargeable batteries, it can also be applied in pseudocapacitors, phototransistors, plasmonic light harvesting platforms, dye-synthesized solar cells, and artificial photosynthesis. So continuation of that, energy storage systems made up of reversible redox couples are two. This is redox flow battery and lithium ion batteries. So they are attractive. Incorporating quinone into batteries are attractive because of three reasons. Relatively high redox potential, which ranges from 1.8 to 3.1. The batteries we use in our phones we know to be at 3.7, so this is comparable as such. Also lower molar mass and high theoretical charge capacity of up to 500 milliamp gram, comparable to inorganic cathode materials, e.g. lithium iron 2 phosphate. So we know these inorganic materials to be harmful to our environment. So incorporating quinone would reduce that harm as such. So two moieties of quinones have been utilized practically in redox flow battery, and hybridization has taken place using sulfonic, which we can see here. Also this one we have sulfonic, which has been used. Also this other one we also have sulfonic. So other trials are underway to use them practically, but two of them has been hybridized using sulfonic. Conclusion, finally, quinone aspires the advancement of man-made energy devices. Quinone and its derivatives are preferable, fabricated rechargeable batteries due to four reasons: relatively high energy density, fast charging rate, solubility in electrolytes, and also abundance and cyclic stability. So a number of issues have to be addressed, which we have found out to be: one, anchoring or crafting of quinone through polymerization, also covalent bonded hybridization, and also using of solid electrolytes. Such efforts hopefully will make the engineering of practical and sustainable energy storage batteries. So thank you for listening to me.
Thank you, Cosmos, for your presentation. So members, we are open for one or two questions because of time. So if you have any pressing question, Dr. Chola.
Thank you, Prof. Cosmos.
Yes.
In your presentation, actually, yes, on this slide, you're saying you're doing a review, eh?
Yes,
but,
yes.
In my opinion, you didn't review enough literature. For example, if you go to your slide number 6, you can just scroll down to slide number 6. I think you're saying there that you're actually talking about that there is actually few, you're calling them few literature has been computed on this topic, for example. You know, such a statement means that energy storage devices probably using quinone, you wanted to say, yes, your first statement, a few computational research studies to date. But I've just done my search here. And, this topic has been researched from 1985. So I was not sure how broad was your library or how many literature. I was actually wanted to see down there how many research publications or books that you actually reviewed, but you didn't include. So when you have this statement in a review paper, I think important to tell us exactly where you got such statement. And then to your next slide, please. In your next slide, you're talking about DFT findings when you're going, but you didn't again tell us what is DFT, for example. Is it discrete Fourier transform, for example? Is it functional? What is DFT? Yeah, you left us wondering exactly what DFT is. So in my, can I ask what is DFT according to you?
Density functional.
Density functional transform, the density Fourier transforms.
No, density functional.
It's the density functional theory.
Yes, yes.
Okay, but you see, it has nothing to relate to what you're talking about before then. Eh? So there was actually a complete disconnect, in my opinion, from what you're talking about from the beginning of this particular slide here. So I think you can do something about making your workflow so that you don't lose your audience. Because probably me, you lost me long time ago. Thank you, Professor.
So thank you, Dr. Shola, for your comment. So Cosmos will take that into account. Anybody else, Dr. Kiptimo, Dr. Korir? Dr. Korir, you had a question? Maybe raised his hand by mistake. So thank you, Cosmos, for your presentation. And I think if there are no more questions,
I can stop my sharing.
Yeah, you can stop your sharing now.
Okay, thank you.
Okay, then I think we will move to the next presenter. Geoffrey, is he available?
Yes, I am. Good
Geoffrey
morning, members.
Sebabi?
Yes, I'm here.
You can start the sharing of your screen.
All right. Good morning, members. This is Mutumba Geoffrey, an assistant lecturer in Chambago University, Department of Economics and Statistics. I'm also a PhD student in Makerere University Business School, doing a PhD in energy economics. I hope you are now hearing me. Our topic is electricity consumption and economic growth in Uganda between 2008 and
Geoffrey, have you started sharing?
Oh, yes.
Sharing the screen. I think I'm not seeing the screen.
You are not seeing the screen as yet.
Members, can you see the screen?
No.
I cannot see the screen. Not yet.
Not yet.
Sharing,
Hello.
Not yet.
Not yet.
So Caroline, can you guide him through the sharing?
Yes, I can guide him through. So
share screen.
Yes. Can you see share? Can you see
Yes.
Yes, click on
I
it.
clicked on it. It went to share your screen. Your
Yes.
entire
Then
screen.
is your presentation open or is it because
My
if the presentation
is open.
is open, just choose it from the open windows down there. They are open windows. Just click on it. Then it will share. No, yeah.
Click on the open windows.
Yes, yeah, it's now starting to share, but you can see your face. You've shared your face. Echo. You can stop sharing. Then let's start again. Just click on share.
Share.
Then browse. You can click on browse to go look for the document or the PowerPoint presentations that you want to share. Just go to browse. Then it takes you to. You go to the location where you saved your item.
Desktop. Can you just get assistance from?
Yeah.
Okay, I help you.
Okay.
Yes, it has shared.
It's trying to share. It has?
It had shared. I don't know why it has just stopped. Just share it again, please.
Trying to restart.
It's not here.
Share screen.
Is it saved?
Yeah, it is.
Because I'm not seeing it there. It has to be just hang on a little.
Trying to save it so that we can.
Where is the? It is this. It's not coming. It's supposed to appear here. Let me save it away.
Okay. Are you on the Teams app? Hello?
Yes. Hello. I am.
Just a minute.
Okay.
The what? Just hold, let me first save it. Okay, I see. Replace it, yeah?
Browse. Say browse.
Yes, look for the document and then you just open it.
When we say sharing,
it
should be coming here. Okay, screen share, desktop.
Hello, have you opened the document? Is the document open?
The document is open,
Yes.
yeah?
Okay,
Share.
now go to the Teams app. Go to the app, the Teams app. Okay, are you in the Teams app?
Because now I'm on slide show.
Yeah, it has shared. It has shared. It's okay.
All right. Okay. Tumba Geoffrey is my name, and our topic of study is electricity consumption and economic growth in Uganda between 2008 to 2018. So earlier introduced myself, Mutumba Sebavi Geoffrey, an assistant lecturer in the Department of Economics and Statistics in Chambogo University. Also, a PhD student in Makerere University Business School, pursuing a PhD in energy economics. My supervisors, there's Dr. Susan Watundu, there's Dr. Thompson Odong, there is also Professor Muiwasam Adaramola from Norwegian University of Life Science, but also Jacob Otim, part of also a PhD student. This is the layout of the paper. And so I will straight away go into the introduction and motivation. Uganda's economy has been growing at an estimated average of 4.9 of GDP per year for the period 2008 to 2018, while energy consumption has been growing at an estimated average of 7% per year. So you realize that energy consumption is growing faster. And when we go into output comparing elasticities, you'll find that energy is growing faster than the average for GDP. But the question there is, what is the direction of causality? Now, there's an observation by Paul and Bhattacharya that electricity consumption is an important driver of economic growth. Most production and most consumption actually depend on energy. Energy is a key input for production and therefore a key driver for the economy to grow. The direction of causation between electricity consumption and economic growth has significant implication, as noted by Asaf and Ajay 2000. It's not possible for one of the rates to grow highly without affecting the other. So for you to keep a high rate of economic growth, you must also sustain a high rate of electricity consumption. So the two must be kept in tandem. Unfortunately for Uganda, this has not been clearly studied. The direction of causation, the direction of causality has not been carefully studied. There are only about 3 studies. We saw one by Maweje and Maweje 2016, which looked at electricity consumption and economic growth, and looked at sectoral studies and agriculture, service, and industry. It showed the growth hypothesis for industry, and it showed the neutral hypothesis for agriculture. Then there was another one by Senkatsi and Okot, who used the autoregressive distribution lag and the Granger causality, used the data for 1981 to 2013. And these findings confirmed the existence of a long-run relationship between electricity consumption and economic growth. In addition, the Granger causality tests confirmed the conservation hypothesis in the short run and a feedback hypothesis in the long run. Okay, having done that, for Uganda, they still need to have greater focus on it. But the literature on electricity consumption and economic growth has been studied right way back from 1978 by Kraft and Kraft, who was studying the American economy, and quite a number of studies have been done. But the results are inconclusive, and the debate has not been concluded yet. So when we go into the literature, I will highlight more on that. There are 4 testable hypotheses that have been presented. The growth hypothesis, which suggests that the relationship, the direction of causality runs from electricity consumption to GDP. And once electricity consumption grows, GDP also grows. And any measures that seek to reduce electricity consumption will also negatively affect the growth of GDP. Then we have the conservation hypothesis. In the conservation hypothesis, it shows that the relationship runs from GDP. The direction of causality is from economic growth to energy. And therefore, here we must carefully look at those measures from GDP that cause energy to grow. And any efforts to try and conserve energy here will affect GDP. And then the feedback is a bidirectional causality, that economic growth causes GDP, and the GDP in turn also causes electricity consumption. Then the neutrality hypothesis is one that, since energy makes a small contribution, then there is no significant relationship of causality between the 2 variables. It has been previously shown the direction of causality running from GDP to electricity consumption. Remember, that is the conservation hypothesis. And the studies, as shown by Ama Tego, 1990, Cheng, and Omei, really attest to this, the conservation hypothesis. Some researchers are showing the feedback hypothesis, and that is the bidirectional causality running from electricity consumption to GDP and vice versa. And we have examples there. However, others found causality running from electricity consumption to GDP. This is the growth hypothesis, and the examples we have seen there: Magazino, Tegiade, Smith, and Papiers, 2014. Other studies are for the neutrality hypothesis, since they find no causality between the 2 variables. Menigak and Otzak is showing that. This study will use a bidirectional causality, so it will use a feedback hypothesis between electricity consumption and GDP, and it seeks to make a contribution to this. Its contribution will be on the multivariate framework of analysis, which seeks to put many variables together rather than the bivariate, which only looks at electricity consumption and economic growth. This one will go ahead to use labor and capital as control variables in our model, and so it will adopt a neo-classical growth model as by Robert Soro. So what are the aims, or what is the aim and objectives? The aim of our study is to investigate the relationship between electricity consumption and economic growth in Uganda. Thus, the objectives is to establish if there exists a short-run relationship between electricity consumption and economic growth in Uganda. Then establish if there exists a long-run relationship between electricity consumption and economic growth in Uganda. The study design used time series analysis, and the data used the quarterly secondary data for the period 2008 to 2018. The data for the period was quartalized using a quartalizing tool, and the data sources were electricity consumption from Electricity Regulatory Authority in Uganda. This is the body mandated with regulating electricity consumption in Uganda. Additional data for GDP and real gross fixed capital and labor force was got from the World Bank statistics. The theoretical model used was the neoclassical growth theory by Robert Solow, 1956, and later modified 1987. It used the ordinary least squares regression, and equation 1 there has been shown, where you have Y being GDP, then you have E being electricity consumption, K being capital, L being labor, then you use the error term, then alpha and delta there to represent the stochastic and the fixed term effects. Then we have the econometric model. Our study used the vector error correction model for long-run co-integrating equation, as shown in equation 2. We converted the values to logs in order to stabilize the means. We took log values, and in the short run, the model was not stationary. We looked at the means. The model was not converging in the short run. That's why we suggested a Johansen co-integration test. And now we're going to look at the diagnostic tests that were carried out. The unit route was carried out to find a stationarity, and we used the augmented Duca-Fuller and the Phillips-Perron test. Then for the functional form, we used the Ramsey reset test in order to find a specification of our model. For the long-run relationship, we used the Johansen co-integration test. That was then to find the stationarity of the error terms, we used the heteroscedasticity, the H test, and normality, we used the Jack-Berer test. What were our findings? From the theoretical model, we have the log. We found the results, and the results indicate electricity consumption, labor and capital have a positive and significant effect on GDP at 5% level of significance. Further, a 1% increase in electricity consumption leads to a rise in GDP of 3.2%, while a 1% increase in capital leads to a rise in GDP of 75.7%. Now those are elasticities that we are giving, while a 1% increase in labor leads to a 4% increase in the leads to a 4% rise in GDP. This is in agreement to earlier studies that have been shown by IRES, by Lindenberg and Dietmar, and also by Stern in 1993 and 2004, who alluded to energy. Although electricity consumption has a small cost share in terms of elasticities, but it has a significant output contribution. So that is now why it's only showing 3% in the output elasticities, and yet it does significantly affect. When we looked at the Granger causality, this is what we saw, GDP. When you see the chi-square, we can see there that what is explained is 91%. And then when we look at electricity causing GDP, we can see the 16% there, leading to 68%. So that is where now we came up with that conclusion of a bidirectional causality. Now that vector error correction term, we are determining the lag length at 3. And when you look at how long the model takes to converge, we establish the optimal lag length as 3. And you can see that that's when in the model, the lag electricity coefficient comes down to 0. Conclusion and recommendations, we say there is a bidirectional causality, implying that increasing electricity consumption increases economic growth, and economic growth in turn increases electricity consumption. Therefore, this paper now made recommendation to Ugandan authorities not only to develop energy policies geared towards expanding electricity infrastructure to increase electricity consumption only, but also address key drivers of energy consumption to support economic growth. We realize that industrial energy consumption is driving the economy, but we have very poor communities with a low income per capita. So there is an important, and there is need to provide subsidies both to the consumers, but also to some of these producers, because most of the extra large industrialists are foreigners. There's a need now to support a local production by subsidizing the small scale industries. Okay, so that was our findings and conclusion, and that brings us to the end of the study. Keep your hope alive, keep energy science alive. Thank you for listening to me. It was Mutumba Geoffrey presenting.
Thank you, Geoffrey, for your presentation on the relationship between electricity consumption and economic growth in Uganda. Now I think we'll be open for questions, and I can see the first question is from Dr. Chola. Dr. Chola, go ahead.
Thank you, Prof. Geoffrey, can you go to the slide with the chi-square values? I couldn't get the slide number. It's around slide 10 or 11. Anyway, as you go there, you are trying to mention that the percentages you have there for the chi-square values, you translated them as the values that your models are explaining. Why did you consider to use chi-square values and not the R-square value? Because actually, well, the chi-square value is a number that tells you how much difference exists between your observed counts and the counts you would expect if there is no relationship at all. Yes, these values here. These values have nothing to do with how much of your that your model is explaining, how much of your results the model is explaining. But the chi-square value should only tell you the statistical difference. For example, when you're considering your hypothesis, the one you mentioned at the beginning, again, you didn't tell us which one is the null, what was the null and what was the alternative. But your hypothesis could have been explained by the chi-square value, not the results, not how the proportion of your results from your model. So what was the R-square value? That's my question, actually.
Well, that is, I'll go and push it in. I now use the R square, not the chi.
Exactly. Yeah, exactly. Because when you use chi, the way you explain it, it's a bit misleading. Oh. Then can you scroll up to your slide number 6, I believe?
Yeah, methods.
Slide number 6. Yes, you're talking about your method. I think I noticed something there.
Theoretical and econometric model.
Yes. I think I had a problem with your models. There's something you're mentioning that you're actually quoting an author that developed a model in, yes, here. In unit number 1, theoretical model neoclassical growth theories by Solo 1986 and 1987. I just want to inform you that this model from 1987 has really changed. Because when you're talking about 1956 and then 1987, in my opinion, you're actually trying to suggest that the development of this model stopped over almost, this is over 30 years ago. There is actually a way that you can get new models, because you're talking about a neoclassical model. There are better and newer models that you can actually refer to in this particular case. So please, can you look at very new literature and quote them here? And finally, if you allow me, Mr. Chair, what was your sample size?
I used secondary data,
Exactly.
and that was already data available for the 10 years.
Okay.
So since I was using secondary data, then I not take samples. Yeah, thank you very much. There was a question on the theoretical model, the newer models, and that particularly I looked at the linear exponential model, but those are extensions to the neoclassical growth theory by Robert Solow. And now the current debate is on renewables, and indeed electricity is a renewable energy. My data here and my intention is to look at the multivariate framework, and we can't run away from this neoclassical growth model. The linear exponential that was developed by Kumel and later improved by other people like Dietmar and Ayres still try to show elasticities.
Geoffrey, I think you're losing me. Geoffrey, excuse me. I just asked you the final question. What were your data points? Well, 10 years. We are talking about quarterly secondary data for the period for 10 years, 2008 to 2018. So were you taking every year one case, every year, or quarterly 1 year? You know, the way you actually took your data is also not clear from your presentation.
There were 44 data points.
Exactly.
Each year had 4 quarters, and that's giving us 44 data points. The data was quartalized using a quartalizing tool. And so each year gave us 4 points, and later it was now run. All of it was quartalized. That's why we are saying quarterly secondary data for that period. But you also realize the data limitation in the Electricity Regulatory Authority. They had reconstructed the data, and the data available that could accurately be traced is one from 2008 to 2018.
Okay, thank you. Let me make it a comment. I think if you presented to us the R-square values, we could have not been worried about the errors in your sample size. So I think it would be a good way to also present for us your ANOVA analysis, so that we get actually the view of how much error was in the analysis. Thank you, Chair.
Thank you, Dr. Chela, for that those contributions, and thank you, Geoffrey, for your presentation. I think unless we have any other question, anybody else with a question, because I cannot see any raised hand and I cannot see any questions in the chat. So then I think, Geoffrey, thank you for the presentation. I think we have come back to the end of that.
Hello everyone, I'm Wagan Sharmasi and from University Department of Mechanical, Production and Energy Engineering. I will present you the experimental investigation of thermal efficiency enhancement of improved biomass cook stoves. So welcome to my presentation. I will start from the introduction part. Cookstoves are commonly used for cooking and heating applications, mostly in the rural area of the countries, and they can be categorized in two ways: traditional and improved one. So the improved cookstoves are the part of the traditional cookstoves, which with scientific techniques, and basically they are shielded fire, and traditional cookstoves are commonly called open fire. So the difference is here: the improved biomass cookstoves has low fuel consumption with high thermal efficiency, and also the cost of the cookstove is low compared to the other. So more than the half of the world population, mostly developing countries, are rely on using biomass as a primary resource by using as a feedstock like animal dung, crop waste, charcoal waste, and somehow rice husk and coffee husk. Also sawdust as they used as a feedstock, but those feedstocks need some special applications like fan. So more specifically in Africa, in sub-Saharan Africa, more than 80% of the population are rely on biomass as a primary energy resource. And when you come to Ethiopia, since the case studies in Ethiopia, more than 8% of the population live in rural area, and they use the biomass fuel as a primary feedstocks. And also Ethiopia, as the research showed, Ethiopia will expect to rely on biomass fuel as a primary resource for the coming number of years. So globally, burning of biomass for cooking purpose will not end. So the only solution is to improve and introducing the improved biomass cookstoves to reduce the hazards which comes from the inefficient way of burning. So due to the inefficient way of burning or burning of biomass fuels poorly, the annual days in the world, as this research, the WHO research showed 4.3 million people are exposed to days because of indoor air pollution. So to reduce these problems, it's better to develop the improved biomass cookstoves to produce a cleaner gas. In addition to health problem, those traditional cookstoves has a drawback in thermal efficiency. That means they have low thermal efficiency that increases the fuel consumption and also time of cooking. That means that related to, since the thermal efficiency of the cookstove is low, so a huge amount of fuel is needed to cook the entire food or to prepare the entire food. So the fuel consumption becomes high, and also the loss of energy will be there, since the way of burning is open fire or unshielded. So loss of energy will be there. So because of that, the fuel consumption becomes high, and also the time to cook the entire food becomes high. So the statement of the problem for this study was days of women and children. Basically, women and children are exposed to this problem. Deforestation, that means pressure on the forest to access the fuel, and also reduce the productivity and development of end users. This indirectly affects the productivity of the end users, because since people are waste their time to look for the feedstock, so in other way it will affect the development of those populations. And also globally it affects the atmosphere by increasing the greenhouse gases. The study was written to upgrade the performance of improved biomass cookstoves, and here are the methodology. Mainly the main part of the cookstove was developed from clay soil and wood ash. That means the combustion chamber was built using clay soil and wood ash. That's due to reduce the heat loss through the combustion zone to the external environment. The selection criteria to select those entire materials is based on their low thermal conductivity and availability. As this reference shows, the thermal conductivity of and the availability of those two materials are very, I mean, the thermal conductivity is very low compared to other parameters like cement, and also there are some other insulated materials that are used to build those type of stoves, but the availability of those material and also the cost is also high compared to those two materials. So by mixing those two, the introduced or the proposed cook stove was developed, and some modified parts were there. The diameter of the cook stove, the height of reactor, primary and secondary air inlets, also fuel feeder with supporter and ash removal grate with 15 holes, also the part of the cook stoves. The targeted issues that have been in this entire research was use of locally available raw materials to develop as well as to use as a feedstock, and also simplify the manufacturing process, because since those kind of stoves are used in the rural part of the country, so the manufacturing process must be simple. That and also the good control of cooking rate. That means it's supposed to be able to control the firepower easily without needing any extreme knowledge. And also it must be reduce heat loss to the surrounding during operation. So this is a basic objective of this entire project, to reduce the energy loss to the environment and to accumulate those energy. And also finally it must be improve the overall efficiency of the improved biomass cook stove. This is a proposed into stove under construction. It has some parts. It has primary and secondary air inlets, and there is a grate with 15 holes, and it has a post supporter. This post supporter helps to use different size of pots. That means it's not a fixed size to use pot, so it's possible to use different size of pot, and also it has handle. The handle is made from the same material, because to reduce the burning of to reduce the burning for human body. And the modification increases insulating the cook stove by mixing clay soil and wood ash to reduce the energy which is exposed to the environment through the wall of the combustion chamber. So results have showed the improvements have done in thermal efficiency, fuel consumption, and time of cooking. There are a lot of methods that can be tested the cook stoves. From that, we select that water boiling testing protocols, and water boiling test carried out to measure and analyze the performance of efficiency of the newly designed stove, and result from the test was recorded and analyzed. So from the experiment was conducted using eucalyptus wood as a feedstock, because mostly eucalyptus is common in Ethiopia and it's available in the most part of Ethiopia. So we prefer to use eucalyptus as a feedstock. So the experiment was taken by using eucalyptus wood as a feedstock. And also some apparatuses was used during the experiment, like thermometer with an immersible probe. This is to measure the initial and the final temperature of the water, and weight scale to measure the weight of water and the amount of fuel also, and cook pot also, another apparatus that was used to conduct this experiment. The thermal efficiency is a measure of performance of a cook stove, which can be calculated by energy transfer to the water to the energy liberated by the burning of fuel. So 3 tests have been conducted to calculate thermal efficiency and specific fuel consumptions. So from the 3 tests, those parameters have been recorded: the weight of fuel burned, initial and final weight of water, initial and final temperature of the water, as well as the latent heat of evaporation, this is constant, and heating value of the fuel also there. So from those 3 tests, thermal efficiency was calculated for each, and the average thermal efficiency was taken as a overall thermal efficiency of this introduced cook stove. And this is the formula that have been used to calculate the thermal efficiency of the entire stove. As we can see, the first one is mass of water initially and the P value or the specific capacity of the water. Finally, initial temperature of the water, the mass of water evaporated and latent of evaporation, mass of fuel, and also the calorific value of fuel was there. So by using this formula, we calculate the thermal efficiency from the entire conductor test. And also, in addition to that, beyond thermal efficiency, specific fuel consumption is another measuring element of the performance of cook stoves. So basically, specific fuel consumption it's just the amount of fuel that required to cook the entire food or amount of feedstock that is added to the combustion chamber to cook the entire food or during the experiment to boil a liter of water. So it can be also calculated by using this formula, fuel used to boil the water and also the water that have been boiled. By dividing those those parameters, we can calculate specific fuel consumptions. So from the experiment, results obtained from the conducted experiment show that the thermal efficiency or average thermal efficiency was 46.28%, the specific fuel consumption was 11 grams per liter, and time of cooking is it was 43 to 48 minutes as well. So from the developed model, some improvements have done, like thermal efficiency, easy to construct the entire stove, so it doesn't need any knowledge or external extra knowledge to develop the entire stove. So that's easy to develop those end users easily, and also it's possible to the firepower. They can control the firepower easily, and it's able to use different size of hoods. Significance of the findings globally, it can reduce the annual death of people, especially women and children, which is related to inhaling smoke from the simple act of cooking. And it can also minimize the impact of emission gases since the combustion has a possibility to be complete, so it can reduce the emission from the stove. It can reduce the pressure on forests, it can reduce the high fuel consumption and time of cooking. Indirectly, as I tried to express before, it can improve the lifestyle and the development of end users. So the research concludes, based on this study, cook stoves are worth promoting rather than open fire due to its higher thermal efficiency and lower indoor air pollution. And it presented a clear view of the improvement in efficiency of biomass cook stoves. And some parameters are also modified. Thermal efficiency, fuel consumption, and time of cooking are improved compared to the previous works, and also it can be used anywhere since the developed cook stove is portable. It's possible to use anywhere, and it can use different feedstocks or different solid biomass fuels except rice husk and sawdust, because those feedstocks need fan to combine the fuel with air to have combustion or to have the fire. So, and also it can be used as a charcoal stove as well. So it has two advantages. It can use as a direct burning or burning of wood, and as well it can be used as a charcoal stove. So finally, we recommend that manufacturing and disseminating this stove will result in a reduced fuel use in rural part of Ethiopia, since the people widely use open fire stove for cooking. So this is my presentation, and those are some references that have been used. Thank you for listening to me.
Thank you, Ganesh, for your presentation on enhancement of the thermal efficiency of cook stoves. So members, now we are open for questions. If you have any question for Ganesh on her presentation, Now is the time you can do it. So Ganesh, as we wait for questions, I'd like you to go to figure 1 of your, I think it was in methodology, page 6. I'm not very clear where you put your fuel. Where do you feed in your fuel? And what is the fuel? Is it charcoal or firewood?
The fuel is eucalyptus wood. But it's possible to use as a cookstop, but the experiment was tested by using eucalyptus tree as a feedstock. The experiment was taken by using eucalyptus, and this is a grade that helps to feed the biomass fuel.
Okay.
Yeah.
Anybody with a question? So if there are no questions, then I think we have come to the end of that presentation. Thank you, Ganesh. You can stop sharing. Did Jacob join us? Jacob Botim? Jacob? So members, it looks like Jacob was not able to join us for his presentation on the effects of gross domestic product and energy consumption on carbon dioxide emissions. So I think then we come to the end of this session. We are free now to join the poster presentations up to lunchtime. And then after that, we can join the joint plenary session for for the discussion on embracing collaborative research. So thank you so much. You may join the poster sessions.
The Energy Regulatory Commission is now the Energy and Petroleum Regulatory Authority. EPRA is established under the Energy Act 2019 and regulates electrical power, renewable energy, and petroleum subsectors. EPRA's expanded mandate includes the regulation of upstream petroleum and coal. EPRA protects the interests of energy consumers and ensures that all players in the energy sector adhere to set business practices. We are here to facilitate access to sustainable energy for all. EPRA, quality energy, quality life.